right. On to actually hypothesis testing. Yay. So we talked about the null hypothesis and the alternate hypothesis on Tuesday, and now we're going to actually use them. So if you get a number, so like we're assuming that most policies are like a 50-50 split. So a lot of times they'll use that as their null hypothesis. In this case, they got their data set as the actual favor is 0.534, so 53.4%. The question is that statistically significant? Is that different enough that we're going to make the claim that it's probably not a 50-50 split? It probably is higher than that. Okay? So that's what we're going to look at today is how do you determine if it's enough of a difference, then we can claim that it's different than that. So, because in this situation, like we could give this one, it's like, okay, it could be 50.2%. Well, technically that's higher, but depending on the data, that could be high enough. Where in this case, this might not be, depending on what other information we have. So, we're looking for a situation where the observed results would be unlikely to occur given the null hypothesis or given the assumption. If that's true, then it's statistically significant. So, if we look at that data, we have two pieces of information that we need to be able to find, or a few things we need to be able to find for proportions. So the first thing, we need to make sure that n times p times 1 minus p, that has to be greater than or equal to 10. If it's not, then we cannot consider the numbers to be normally distributed, and we have to do some other things about it. So in this case, I have 1,000 times 0.5 times 0.5, which is 250. So it checks that box. The next thing we want to find is our mean and our standard deviation. The mean is my null hypothesis. So in this case, my mean is 0.05, or 0.5, sorry. My standard deviation was that formula. So the p, so it's going to be the 0.5 times 1 minus 0.5 over n, which in this case is 0.016. Okay. So whenever you're doing a proportion, we need those pieces of information. We need to know our standard deviation, and we need to know our mean. And we need to make sure that that NP times 1 minus p is greater than or equal to 10. So one standard deviation is 0.516. If we go back one standard deviation, you're at 0.484. Next one. So is one standard deviation enough to say something is unlikely? No, because that's 68% between those, right? And what's the typical basis that we've been using for unlikely? 5%. So we want to go at least two standard deviations. So if I go another standard deviation, let's see if they have that there. They probably do. So if we go another standard deviation out, we would be at 0.532. And another one down is 0.468. I was doing 1.6, right? Yep, that's right. Okay. So that's 2 standard deviations away. So is the value that I got in my probability piece 0.534, where would it fall in this? It's going to fall over here, right? But not by much, right? It's pretty close. However, since it's over here, I can now claim that that's statistically significant because it's more than the 2 standard deviations away. Okay. So there's 2 different ways that we can look at this. So the classical approach and the p-value. You will see both of these. And I got yelled at, so I have to teach them both. So, because I used to just teach the classical approach, and I was told I have to show the p-value. So we'll show them both. So the classical approach is looking at standard deviations. We want to figure out how far away from the mean my value is. And if it's bigger than the z-score for that, how many standard deviations or what percentage, then we're good. So in this case, I would find my z-score. Remember, z-score is the value minus the mean divided by the standard deviation. So in this case, my z-score is 2.15. That's bigger than 2. So it falls in that little piece right there. Outside of 2 standard deviations, we're only at about 2% on each side. Because remember, we're looking at both directions here, right? So 2 standard deviations, that other 0.0228 on that side over there too. So that combined is that 5% at that point. So that would be what kind of a test that we basically are looking at when we're looking at 2 standard deviations. If we're going both directions, it's a 2-tailed test, right? So we're there. It's going to be somewhere over there. That would be considered to be a unlikely situation, so therefore we would be able to reject the null hypothesis. So if the sample proportion is too many standard deviations away from the mean, we reject it. And I don't know. Okay, so I'm actually going to get the values for here. T-table. Those 3. Okay. it is, I gotta figure out the two table. So you have yeah. All right. So those are the z-scores. And then those are the percentages you're looking at for two tails or one tails. So remember, the two tails is on both directions. So if we're only looking for one direction, it moves it down a little bit. So in the case we just did, the z-score was 2.15. So it's above the 1.96, which is really the 5%. We estimated it to be 2 just to be able to do the easy calculation, but in reality, we would use the 1.96. So that's bigger than the 1.96, which would give me that 5%. If I only wanted to look in one tail, because in essence, I really just wanted to know if it was higher, right? In that situation, my z only had to be higher than the 1.645, because that's that 5% right there. So it's even a lower bar because now my entire 5% is now on that one side instead of split between the two sides. So that's why when you're looking at one-tailed and two-tailed, that's going to matter because that percent's going to change. So that's looking at the classical method with the z-score. The other way you can look at it is with the p-value. So the p-value is comparing it to the percent in that section. So again, we're still looking at where it falls. Okay, that's not going to actually change. The piece that's going to change is the last part. So we're then going to figure out what the probability of that occurring is. So what's the probability that the z is greater than 2.15 and it's 0.0158? And you can get that from the tables, which you're not going to have to do. We then compare this value right here. So that's my p-value. And we're going to compare it to the value that we're going to look at, or whatever my significance level is. So typically your significance level is going to be that 5% or whatever, however we're looking at. So if we're looking at it in terms of 5%, that 0.0158 is definitely greater than 0.05. So again, I'm going to reject. So those are the two different ways that we can look at it and compare it. So, oh, yeah, you're right. Good catch. That's smaller than that. Good catch. All right, so if we look here, I'm going to actually use mine to do this now. 534, my sample was 1,000. I'm assuming it's that. So two different ways we can do this. This calculator is A20 or 32. If they give you the proportion, you can use the proportion. If they don't, they give you the actual calculation, the X value. You can type it in here and actually it will do the calculation for you. We would set up my hypothesis to be whichever way, my alternate hypothesis is the way that I want it. So in this case, I'm going to look at greater than. So I'm going to look at a right tail test. This will do the calculations there to make sure that it actually works, that they're above 10. it will figure out your standard deviation. Notice my 2.1503 is still there. And notice how it falls in that red region over there. That's when I know I'm going to reject. Depending on what the questions ask you for your homework and depending on how you want to write this, it gives you both. It's in the rejection region because it's greater than the 1.96, and the p-value is less than 0.05 to 0.153. So the goal, or what you're looking for to reject, is that it falls in that small region on the tails. If it doesn't, we fail to reject. And in this one, if I changed this to this 53, I'm now failing to reject. So that 0.4% actually made a difference. Okay? So 53% would not be statistically significant enough to be able to reject. Oh, I know why. That graph is wrong. I got to fix the graph. It's always showing two tails. Yeah, I got to fix the graph because it should have been back here. Carolyn, you didn't catch that. That's okay. So if it was this in a two-tailed test, you can see right here, see how it comes up and says fail to reject. So it will give you that criteria there to make your life a little bit easier. All right. Let's look at the next one. All right. Testing your population. For every problem, here's our steps to do this. Step 1, we need our null hypothesis and our alternate hypothesis. You need both of those. Okay. Step 2, you need to know what level of significance you're going to test at. The vast majority of cases, not every case, just the vast majority of them. The A will be 0.10, 0.05, or 0.01. Those are the vast majority of cases will be those three. Okay, most of them will be that 0.05, that 5%. And remember, that is the probability of me making a type 1 error. So the lower that, the less chance that I'm going to make that type 1 error. Also need to make sure that your n times p times 1 minus p is greater than or equal to 10. So make sure that that is greater than 10. Okay. And the sample values have to be independent from each other. So in essence, the sample size is less than 5% of the population. Once we've got that, we calculate our z-score. That is your value. So that's the probability that I'm getting. So that's my test. That's the null. So the null is that p0. This will give you your z-score, or my test statistic. And then we compare it. So we're going to compare it to the z, or if we're going to do the p-value, we have that one extra step to calculate the p-value. So we're either going to compare the p-value to my test statistic or compare the z-score to the critical value that I have. Which is why I always hated having to do the extra step for the p, because you really have to do an extra step to find the p. You automatically have the classical value approach. You have to do one more step for the actual p-value. However, and she had a really good point when she complained about this. In most of your social sciences field, psychology, sociology, those things, they use p-value. They use p-value all the time. So knowing where that comes from is actually important. So we will look at both. It is fine. In the end, the result's the same. The rejection or not rejecting will be the exact same no matter which number you actually use to compare. That's not going to actually change. All right, let's do some problems. That's all the rest we're going to do today. All right, step one. Null hypothesis, alternate hypothesis. We're talking about proportion here. So that's the p hat. What's going to be my null hypothesis in this case? The 0.08. It's right there. So this is a known proportion. So that's what I'm comparing it to. So what's my alternate hypothesis? What are we trying to determine? Yes. Yeah, so they say, does a sample of evidence represent significant evidence that a higher proportion of subjects receiving it? So higher would be greater than the 0.08. So that's the first thing we want to do. Next, we want to make sure that we can do this. So that's got to be greater than 10. So n was 705, 0.08, 1 minus 0.08. So we got 51.8. So 52. So that's definitely greater than or equal to 10. So we're good. All right. My significance level is 0.05. Is this going to be a one-tailed or two-tailed test? One-tailed. Right or left? Right-tailed. So my significance level, I always forget how to make that. That's fine. And it's a right-tailed test. Okay. Copy? Yes, good. All right. Actually, I'm going to leave. So now I got to find my pieces of information. So let's go over here and use this. So in this case, do they give me my proportion, or do I have to? Do they give me the data? They give me the proportion for the null hypothesis that we're comparing it to. But the actual test data, did they give me the proportion for it, or did they give me the data to calculate it? Yeah. If you look, that's the null. That's the significance level. There's no other proportions in this problem. Okay, so I've got to be able to calculate it. So when we're looking at the calculator, I've got those two pieces in it. So in this case, I'm going to use the count. I'm going to put in the x value for it. And they said 66 people, so we'll put 66 there. At a 705, so 705 there. My hypothesized thing is 0.0. And a significance level of 0.05. And we were doing a right tail test. So when you're doing your problems, this is where you're going to check and make sure that you're doing the right ones when you type it in the calculator. You want to make sure your hypothesis matches the hypothesis here. Okay? So my null was equals 0.08. My alternate was greater than 0.08. It meets the criteria. They're above 10. My sample proportion was 0.0936. So my test statistic, or my z-score, was 1.3327. So that's right there. So it is not in the rejection region. And the actual value, which that should have said, was 1.645. So 1.3327 is not greater than the 1.645. So it fails that. And if we look at the p-value, the 0.0913 is bigger than the 0.05 when we want it to be less than. So in this case, I'm failing to reject. So what does that mean in terms of this problem? So the test you're going to have, okay, because in essence, this test is basically a true or false. It's either you're going to fail to reject or you're going to reject. So that's not what I'm looking for, because you can guess 50-50 and do well in the test. Okay. The biggest piece to this test is being able to figure out the null hypothesis and alternate hypothesis, and then being able to write the conclusion based on the information they gave you. That's going to be the biggest part of this test, is the conclusions. All right. So we have failed to reject the null hypothesis. So what does that mean in terms of this problem or this situation? What can we say? Yeah.
That was a type 1 error?
No, it doesn't necessarily have to be a type 1 error. A type 1 error just means that a type 1 error is where we reject, but we shouldn't have. So we didn't necessarily, and that's why I hate the term the errors, because we didn't make an error in this case. So we didn't make a type 1 error, we didn't make a type 2 error. We just failed to reject the hypothesis, which means in this situation that the new medication that they're using, I do not have sufficient enough evidence to state that the drug has a higher percentage or a higher proportion of nausea. Okay? It's not significant enough to show me that there's a higher percentage of nausea with this medication. That's what this is saying. So even though it came out to be, what was it, 9 point, what was the actual value? Yeah, it was like 9.4%, right? Even though that was at 9.4%, that's higher than the 8%, right? But it's not significantly different enough for me to claim that the 8%, that it's higher than the 8%. All right? Does that make sense? Because that is literally the most important part of statistics. Out of everything we've done, that's the piece that's important. And that's the part that a lot of people don't end up liking, because you do all this work, and I don't know why they would have wanted more nausea for this drug than not. But my guess would be that they were not Humira. So Humira would be very happy with this result. However, whoever was doing the trials probably was trying to show that it's worse. So they're not going to be happy with the results. Okay? So that's what you have to be able to say. You have to be able to take what they gave you and then make that conclusion on it. That's what you have to do with your projects. When you look at your projects and you look at your hypothesis at the end, you're going to have to say, are you going to reject the null, or are you going to not reject the null, and that your data might not have been significant enough. Okay? And you have to be okay with that. Your hypothesis basically could have been wrong. That's fine. That's okay. All right, let's look at that one. I always get a kick out of when the Pew Research does gun laws, because I hear pew pew from the cartoons. Currently, 53% of Americans believe gun laws should be stricter. The Pew Research Center surveyed 780 randomly selected Americans with at least a bachelor's degree and found that 457 believe that gun laws should be stricter. Does this result suggest that the proportion of Americans with at least a bachelor's degree is different from the proportion of the general American population when it comes to belief about stricter gun laws? And they want to use a 0.1 level of significance. All right, so what is my null hypothesis? Yep. My alternate hypothesis? Less than, greater than, or not equal to? Huh? Not equal. Somebody other than Caroline, why did she say not equal? Right. Different from. Okay. All right. So, and my level of significance for this case is 0.1. And in this case, again, they didn't give me another percent, so we're going to do the X value. So we got 457, 780, 0.53, and we're doing a 10%. And it is a two-tailed test. So requirements are met. It's greater than 10. The proportion of Americans with at least a bachelor's degree that thought we should have stricter gun laws is 0.59 or 5859. So the z-score is 3.1279. So just looking at that, are we going to accept, or are we going to not reject the null hypothesis, or reject the null hypothesis? What does the data show right now? How many standard deviations away from the mean is it? 3. 3.1279, right? Okay. What's the general number that we've been always looking at? 5%, or it's 2 standard deviations away, right? And actually, this is not 5%, this is 10%. So it's going to be even lower than that. So based on this, do you think we're going to reject or not reject? Yeah, we're going to reject. This one's way over there. Okay, so we are going to reject in this case. All right, so what's my conclusion? What doesn't? So, okay. So, yes, very clinical answer. So, use the actual problem to state a conclusion. Because this is what you're going to have to do with your project. You're going to have to take it, you can't just say, I'm rejecting the null hypothesis. It's got to be related back to your project. Okay? So, here's this what they're looking at. So what's the statement? What's the sound bite that the news anchor is going to say? Because they're not going to get on the news and go, "We've rejected the null hypothesis." Well, the Pew Research Center did the study, not the 53%. The 53% was what they're basing their study on. Okay. What are they looking at?
The bachelor's degree.
Bachelor's degree.
Yeah, I'm just trying to figure out how to word it. Because I'm like, it doesn't matter if you have a bachelor's degree. It's basically kind of somehow you have to say that into
Yes.
the answer. Yeah.
So they have determined that the proportion of Americans with at least a bachelor's degree support stricter gun laws than the average American. That's what they would say. Okay? And now, that one statement, now depending on the news channel you listen to, will change that. Okay? Depending on who they're actually talking to. So, this is why I say statistics is the thing you can lie with. So, one channel or one side would say exactly what I just said. The proportion of those with a bachelor's degree support stricter gun laws. The other side will say those that lean more liberal and are highly educated support stricter gun laws. So, because they associate liberal and highly educated. So, Was either one of them wrong? Nope, they both said the exact same thing. Okay? It's just a matter of how they presented it to form the opinion of the person that's listening to it. Okay? Now, we did a 10% or 0.1 level of significance. If I change this to do a, like, okay, we're going to change this and do this as a 0.01, the highest level of significance I can do, it still's rejected. Okay, it's far enough out there that even at the very highest end, we would still be rejected. So it is quite significant there. All right. We can also look at it using confidence intervals. So confidence intervals are in essence a two-tailed test. Okay, they're exactly the same thing. All right, so a confidence interval is just going to give you these two values here, and if it's outside of those two values, we're done. We know we're rejecting. So all the confidence interval is going to do is give me that breakpoints. Okay, so you can do it with confidence intervals as well. All a confidence interval is a two-tailed test. If, so one of the big pieces that we looked at originally, hold on, it didn't put the right slide there. This is the slide I want. All right, let's look at this one. According to Cellular Telephones Industries Association, CTIA, 72% of all adult Americans would rather give up chocolate than their cell phone. Tanisha conducted a survey of 35 randomly selected teenagers, aged 13 to 17, and found 28 would rather give up chocolate than their cell phone. At a significance level of 0.1, is there evidence that the proportion of teens between the ages of 13 and 17 who would rather give up chocolate is higher than the percentage of adults? Okay. What's my hypothesis? What's my null hypothesis? So proportion is equal to 0.72. The null hypothesis. The null hypothesis has got to be the same. The alternate's got to be the same as the null hypothesis. It's just got to be a different symbol. So are we talking less than, greater than, or not equal to? Yeah. Because they're talking about higher than. So it's greater. Okay. So 28 out of 35. 28, 35, 73, right tails. The requirements are not met. They're not greater than, it's not greater than or equal to 10. Which means I can't do it this way. Okay? So if, this is important. So like if it doesn't meet this, all the rest of the stuff doesn't work. Okay? So it's got to meet that criteria there for it to actually work. So if that doesn't work, we need to do what's known as our binomial process that we did before to figure out the percentage, the random chance that that would happen. So I want my p-value, to be x is greater than 28. That's what I'm looking for. So we can go back, and that calculator is, where's the binomial? 22. So we did 35 trials. The probability is 0.8. And we had 28 successes. Oh, sorry, the probability is 72%, sorry. 72%. So I want greater than 28. So look here, greater than 28, or actually they say greater than or equal to 28, is going to be 0.1953. So my p-value is 0.1953. How do I compare the p-value? What am I comparing it to? What was my significance level for this one? 0.01. So I'm going to compare that is greater than the 0.01. So I fail to reject. So even though it was 0.8, it's not significantly different than the general population to accept it.
What was the number of that calculator?
22.
22.
Yeah, this one's 22. And the only time you need to use this one is when the requirements are not met here. That's the only time you need to use it. In a 2004 survey of undergrad students in the United States, 89% of them responded that said they owned a cell phone. In a recent survey of 1,200 randomly selected undergrad students across the United States, it was found that 1,098 of such students own a cell phone. Is the proportion of undergrad students who own a cell phone now significantly different from the 89%? And we're going to use a significance level of 0.02. So, null hypothesis is what? Is equal to 0.89. Alternate hypothesis is not equal because it's different from. And my A is 0.02. My N is 1,200. And I think I used X. Yeah. And my X is 1098 for this one. Oh, and I don't have 0.02. All right, I can go fix those when I get out of here. All right, requirements met. We're good. We're at 2.768. And means we're over here. We're in the reject region. So what does that say about students now compared to in 2004? More of them own a cell phone. So we're at 91%. I think it was now, right? Yeah, 91.5%. So more of them own a cell phone now than before. Now, notice how this one was 91.5% and we rejected, right? That's only like 2.5% higher, correct? When we go back here and look at this one, this was at 72%, and my proportion was at 80%, and we didn't reject. We failed to reject this one. What's the difference between the two? Huh? Sample size. The larger your sample size, the smaller your change has to be to show you a significant difference. Okay, I only did 35 trials here, so it was a very small sample size. I needed a lot larger change to be able to make that claim. Where on this one, the cell phone example, I had 1,200 selected, so that 2% change is significant enough. Okay. So that's again why sometimes the more data you have, the better. The more you can show that significant or statistically significant values. All right. Tuesday's class will be almost exactly the same, except we're going to do it with mean. So the only difference is it's mean instead of proportion. So, but this one goes in, use the t-score because we don't know the standard deviation. So it's a little different with the critical values. All right, any other questions? Okay, I see you Tuesday. I will have the practice sets for chapters 8 through 10 posted tomorrow. I'm not sure exactly what time tomorrow, but sometime tomorrow.
Do you have a question?
Yes.
So here we looked at suggested it was NP,
I know.
MySpeed, and your.
It's just they do it separately.
Yeah. So where does that come from? Like how do
Because
these make sense? I'm just trying to figure out like why it would. Because that one is not NP.
no, that's the other one. So it's they distribute it. It's n times p,
Mm-hmm.
and then n times the 1 minus p. They just did them separately. I'm going to fix that and change it
Okay,
back to the other
okay.
one anyway.
I was just confused whether it.
Yeah,
was
it doesn't
saying the
actually
same
change.
thing
Yeah, it
or-
says it's the
okay.
exact same thing.
Okay. Thank you.
I got to change that. I got to change a few things on that calculator. So, oh no, you're fine.